2.7 is brought to you by old school town Lego guy with his double pocketed button up shirt and red hat. So in 2.7 we're going to put it all together. Okay, we're going to look at a linear and an exponential model and decide which one is the best one to model an equation. So before we dive into this section, let's take a look at a summary of the things we know about linear and exponential stuff. So if I were creating a reference sheet, I would maybe make everything linear on one side, everything exponential on the other, although we don't need that here. I think we can fit it all on one side of the sheet. So linear stuff, first we know that in a sequence of numbers, we're adding a constant. And we call this constant the slope, which is also known as the average rate of change. If we happen to know two values, two ordered pairs, we can calculate this slope as y1 minus y2 over x2 minus x1, which we also know is just simply the change in the y values divided by the change in the x values. And then the model that we use, also we could call it the equation, is y equals mx plus b. This is the slope-intercept version of the line. It's that version because the m represents the slope, just as we noted above, and the b here is the y-coordinate of the y-intercept. We can also think in context, this b is considered the initial value. So the starting value of whatever we're working with this fixed change every time step, fixed change as addition. So then exponential equations, let's add in here one more thing. In Desmos, if we are going to find a regression equation, we would do y1 tilde mx1 plus b, where this y, where this index, these indices here, this y1, x1, they need to match the table. So you would have x1, y1, you could also have x2, y2 there, so you just have to note what table happened. By default, it starts with 1. If you do multiple tables in one graph in Desmos, it'll keep labeling these a different value, x2, y2, and then you could label it yourself as well if you wanted to. This is just the default. So then for exponential, we know that this is multiplied by a constant. And that constant that we're multiplying by turned out to be the relative change. No, it didn't. It turned out to be related to the relative change, okay? And here's the connection. So where the relative change equaled the r. So this constant that we multiplied by was either a growth factor, and it was growth if b was greater than 1. And we calculated b by doing 1 plus r. That's the connection between the relative change. So if we find the relative change, we add that to 1, in other words 100%, and we get the growth factor. It's a decay factor if our b value is between 0 and 1. And then we calculate that by doing 1 minus r. Now, when you use the relative change factor, or relative change formula, that new minus old divided by old, if it's decay, this value will be a negative number, so you would just do 1 minus that value, not 1 minus a minus, right? So this b value, often we think of the decay rate as a positive value that we then subtract from 1. So be careful of that. So then the model, which I've already kind of stated here a little bit, these b values I'm using, is y equals the initial value times some growth or decay factor raised to an x value. As I just mentioned, this a value is the initial value, also known as the y-intercept. And so it's the same, this intercept and the 0, b intercept are the exact same thing. Of course, mathematicians are jerks because we use b as the growth factor, but over here we used b as the initial value for a linear function. So be careful with that, making sure you keep track of if it's linear, the b is totally different than if it's exponential. Really, b and m are the similar concepts in terms of what's happening in the model. So all this b stuff we've talked about up here, and let me just quick do an example of a growth and decay. So let's say we have 10 times 1.05 to the x, as we noted in 2.5. The b value here is a 1.05. Since it's greater than 1, this is a growth function. If we look, and the growth rate, r, or the relative change between in two values, is 0.05 or a 5% growth rate. Whereas if we have, the other one we used in the notes was this. Here our growth factor, which is not a growth factor, it's a decay factor because it's less than 1. This 0.8, that's our decay factor. And our R value happened to be 0.2 or a 20% decay. So if we use the word decay, we ignore the negative. Decay, we understand, is getting rid of that value. One last thing I guess I should have shown for these is the graphs for both linear and exponential. So an exponential graph looks like this. This is a growth function, oops, not 0, greater than 1. And a decay function looks like this. So this is a b value between 0 and 1. And we should label the x and y axes here as well. And then the linear stuff, go back up there and quick draw those graphs. Those are a little more straightforward. Here's a growth, linear growth. Here's linear decay. Linear actually has two other options. An undefined growth, which is a vertical line, and a zero growth, which is a horizontal line. But we didn't really talk about those, and that's not really going to show up in our models. Last thing we need down here is how do we find this model in Desmos? I have not demonstrated that yet, other than through the project videos, and it's just using that formula with the not equal sign. What's wrong with me? Using the tilde function, just like with the linear, but we're replacing the linear stuff with the exponential model. Okay, let's work through the problems then in 2.7.